Hello, we are live.
Hey
Um,
everyone,
Thanks everyone for joining us today. I'm Journey,
and I'm Kailan.
and we are developers on the DevRel team here at Fastly. So yeah, thanks for tuning in. Today we are going to introduce you to Fastly's new Core Cache API. So let's talk about what is Core Cache. Core Cache combines the power of Fastly's Compute at Edge platform with our longstanding delivery services. So it basically gives you the power to cache content that you've generated at the edge. Um, and if you haven't heard of Compute at Edge is our computing platform that allows you to run WebAssembly close to your users. So you can write code in whichever language you're comfortable with and then run it natively across the world. I'm going to hand it over to Kailan to talk about what DevRel does here at Fastly.
Thanks, Jenny. So, as mentioned, we are the developer relations team. But what exactly does that involve? Well, we produce a lot of content, which includes the live stream that you're watching right now. But this also comes in the form of blog posts, code examples, tutorials, and demos, many of which are living on our award-winning developer hub at developer.fastly.com. We also spend a lot of time engaging at events with customers and prospects, as well as creating and maintaining tools that are used to interact with our platform. It's a really great, fulfilling job, and it's so nice to be able to work with the community to spread the word of Fastly.
Okay, and where can we be found? You can find Kailan and I on Twitter and Mastodon, and you can find Fastly Developer on our developer blog at dev.to/Fastly. And we're also on Twitter at Fastly Devs. And of course, you can find us on our award-winning developer hub as well. So, Kailan, what are we going to chat about today?
So today we're going to be looking at the Fastly Core Cache API, which is a brand new API released as part of the Computer Edge SDKs for Rust and Go. Support for other languages will be coming soon. And we're going to be using this to enhance a tutorial that we provided on the Developer Hub quite some time ago when Computer Edge was quite young. So we're going to actually take this tutorial that was written by our colleague Dora and enhance it with the things that we have available to us in the Rust ecosystem in 2023, as well as the Fastly Core Cache API, which is going to allow us to take a lot of the processing power that is happening on every request for this example and just do it once per pop at least. So we're going to literally just start off by following this tutorial. We're going to initialize a Computer Edge project and just start following what's here. The only difference is that instead of using Unsplash, we're just going to be posting images from our own backend. And we're also going to be using a different algorithm for the hash because when this was originally built, it was made with what was available at the time, which was Blur Hash, a very popular library, still holds up very well. But there's a newer, more efficient and also easier to use option now, which is called ThumbHash. And conveniently, there are implementations of ThumbHash in JavaScript and Rust, which are the languages that we are most interested in here. And yeah, it's a really great algorithm. It allows you to essentially take a image of any size and generate a little string that represents how that image kind of looks and feels. And it's just a little kind of blurry representation, and this is really useful for when you're initially loading a page full of images and you don't necessarily want to wait for every image to load in before it looks appealing. So what you can do is actually just load in these thumbnail hashes as part of the initial process and display them while you wait for the larger images to load. It sounds kind of complex, but it's actually pretty straightforward. And you're going to see there's actually very little code involved in this example. So I guess we'll just jump right into it. Jenny, did you have any pre-warnings for our viewers?
Yeah, okay. So the last time that we did a stream, we showed you the full process of creating and deploying a Compute at Edge app. But today we're going to assume that you kind of already know how to get it started. If you don't, you can follow the Getting Started with Compute at Edge link in the description of the stream if you're not sure how to do it. And also, if you've viewed our streams before, you may also know that we've mainly been working with JavaScript, but today it's going to be our first time working with Rust. So all you Rust stations in the audience, get out your little claws because we're going to be using Rust today. It's the first SDK to be supported by the new Core Cache API, and it's also going to be easier and more efficient for us to work with images this way. So yeah, let's jump into building, Kailan.
Let's do it. Okay, so we're going to start the way that we usually start, which is by initializing a brand new Computer Edge project. We'll do it in a folder. We'll call it some hash demo, and we're going to run Fastly Compute in it. Oh, that directory should be empty. Apologies. Oh, I see what I've done. Got to CD in. Wow, we're only getting started and we've already made mistakes.
It's okay.
Fastly Compute in it. We're going to be using the default Rust starter kit. And we'll open that up in our favorite editor of choice. I'm just going to go ahead and remove some of the boilerplate from here. The index page we can keep because we want to show some content in the browser later, but we'll rename it. And we'll just get rid of some of this logic. We still want to match on the path. And we also want to match on the request method. So if you've seen a Computer Edge project in JavaScript or Rust or any language before, this probably makes sense. It may look a little daunting if you're not used to Rust, but this is essentially just us defining a main function where we take a request and we return either a response or an error. And from here, we can match on the path, we can match on the method, and we can make sure that we're forwarding the request to the correct backend or running the correct edge side logic. So the first thing that we want to do is serve our images. So we've got a bucket in Google Cloud, and we're going to use that as our example backend. Because we're developing rapidly, we're going to want to actually set this up in our local testing server as a backend. When we deploy to Fastly later, we'll configure it on the service. But for now, we're just going to create the backend, and we'll call it content backend. We want to override the host header that we send we want to override the host header that we use when sending requests because of the one that Google is expecting, and that is storage.googleapis.com. And we will set the URL to send the request to as well, which is storage.googleapis.com. The next step is to make our requests forward to that backend. So we'll ignore this branch for now and just send all requests to one backend. And I'll define a constant for the backend because this is just good practice. So now we have a response, and we'll just pass that response to the client. This is going to show us a warning right now just because we're matching for no reason, but we'll fix that later. So at this point, if we start this up in the local testing server using Fastly Compute Serve, it's going to build our JavaScript application into a WebAssembly binary, which is ready to upload to the platform. But actually, in this case, we're just going to run it using the local testing server. And let's see. So what we want to do is actually go to one of the images that are on this path. So I'm going to quickly go back to the example because we're using the same images that were used in the original tutorial, and grab one of the URLs just to make sure that we have done everything correctly. Forgotten the name of the bucket.
No worries.
Let me refer to my notes. Sorry for the delay. Okay, got it. So let's go back to our browser and just check that the requests are being passed. Hmm. Oh, okay, it's Unsplash demo images. One of the hardest problems in programming, naming things. And we should also add .jpeg to the end. Ah, okay. Let's just continue on with the demo and hope that it works when we get to it. I'm not quite sure what the issue is here. This is a terrible start.
That's all right. We're
So
here to work on this together.
storage.regulars.com, Unsplash demo. So this is what we should be being served when we go to that path. Ah, okay. Looks like I
There it
just said something
goes.
wrong. That does work.
Right.
Okay. So what you're seeing here is an image being passed through the computer edge service that we just wrote. So the request is coming in from the browser, and we are, in any case, just sending the request to the content backend and then forwarding the request back, forwarding the response back to the client. So now we're going to do something more, which is to host like an index page on the root path. So to start with, we'll just build a response from the static file that is included in the folder here. And we can just use include string. We also want to make sure that we set a content type on this so that the browser knows that it's an HTML page. Yep, the one that's been suggested is correct. We also want to match on the method here. So any GET requests for the root path will return the index HTML page. And let's just verify that that is the case. It is.
Nice. That's our default HTML
Default
page that we
starter
started out
kit.
with.
So let's go in here and actually add some content. So I'm going to spare you writing all of it, but we'll just throw in a few key elements live. So the first thing is that we want to add our first image. So I'm going to actually go ahead and copy this out of the demo that was provided on the Developer Hub. I'll actually copy all of these because these image paths are all unique. But for you implementing this yourself, obviously this would be on images that you already have on pages. So you wouldn't need to, create a demo with a bunch of images. So we'll throw that in. Oh. There we go. And what we'll do is remove the data prefix to these attributes just for now, so we can demonstrate how the page loads without any of the optimizations that we've put in place. You'd probably want to have some kind of process where you're programmatically taking the images that look just like this and replacing them with the placeholder attributes. What we'll be doing later on is adding some JavaScript to take the attributes that are here and use them to load the correct images at the right time. So let's try this one. There we go. We've got a page full of kitty cats.
Beautiful cats. Are these Doris cats?
They're not. They are Unsplash cats.
Oh, I see.
That would be nice, though. I actually suggested yesterday that we should have a Fastly cat library, or
We
I guess
should.
any pets. I don't want to discriminate. I'll throw some CSS in here just to make it look pretty. It also kind of helps to demonstrate the loading effect when that happens later. And it's also useful to have a little header so that when the images appear on the page, they're not fully within the viewport, so they don't get loaded straight away. We'll see how that looks. There we go. So that's what the page looks like. But obviously, all of the images are loading in full, apart from that one, which we'll get to later. And if we look at the network tab, we'll see that there's about 4 megabytes of traffic being downloaded, like 4 megabytes of content just for this page. And I mean, if I just came to this page for this top piece of content or like this top image, it's kind of wasteful, especially on a poor connection, to go ahead and load all of those images. So the purpose of this example today is actually to be able to load these thumbnails in place of the full images and only load the larger images when we need them. So let's go ahead and do that. The first thing is to set these back as data attributes. And the reason we want to do this is that if we have them as a source attribute, then the browser is going to load them immediately. But we actually want to wait until our JavaScript comes along and lazily loads these full images. So we'll go back and we'll restore the prefix to all of these attributes. And you'll see that we have another attribute here, which is data placeholder. And this is going to tell our code later on where to load the placeholder thumb hash from. If you remember, we saw earlier that for each of our images, we generate a string that represents the image. So we need to point our code to where that string is going to come from. And that is going to be the same path that the image is on, but with the prefix of LQIP, which is a low quality image preview. It's a term that I think maybe we've coined. I don't know if I've seen that before. Don't let the .jpeg extension fool you. This path is not going to return you a JPEG. This is merely an identifier so that the computer edge service knows where to fetch the photo from. The data that's going to be returned is going to be in a binary format, and it's going to be the raw representation of the thumb hash. So let's go ahead and implement that endpoint and try it out. So I guess the first thing to do would be to add the thumb hash dependency. So I'm just going to go ahead and run cargo add thumb hash. And there is another dependency that we're going to need, which is the image crate. And the reason for this is that thumb hash will only accept an image up to 100 pixels in size on either dimension. So we can use the image crate to resize the image in case we receive one that's larger than expected, which in our example is all of the images because they're pretty large. So we've added those dependencies. I've done that using the cargo add command, but all this is doing is adding it to the cargo.toml file. You could do that manually if you wanted. And yeah, let's start writing some code. I'm going to shamelessly pull up my reference code so that I don't get anything wrong. And yeah, we'll write a function to generate a thumbnail. So I'll do this outside of the main function because we don't want to clutter up the main match statement. But we'll take in a request. So functionally, this is doing the same thing as the main function is. And we'll just mark this as to do while we go in here and add the match clause, the match arm, I think is probably the right term. And that is as simple. The match clause. I do prefer that. The beauty of these is that you can chain an if statement onto the end of it. So it's really easy to just, match on prefixes rather than just an entire string. So if we receive a request now that starts with LQIP, like these ones here, then it's going to call the LQIP generator function. And inside of that function, we're going to do a few things. So the first thing to remember is that the request path is going to look like this. But when we send the request to the backend for the image, it doesn't know about this. It's going to just want the path of the image. So we're going to Yeah, exactly. And because we know the length of the little prefix, we could literally just trim it by 5 like this. But actually, you'll see that the editor suggested something nicer here, which is trim start matches. So we should be able to just trim off the start. We do want to leave the trailing slash just for the sake of the back end. And yeah, then we want to update the path of the request to the new image path. Oh, okay. I was wrong. We actually have to trim it like this, unless we want to clone it. Although I think we are actually cloning it here as well. This is the beauty of Rust. So we've now updated the request from the client to have the new path that is trimmed. So at this point, we can just send it to the backend and get a response just like that. And we're using the constant that we declared earlier. Once we've received the response, we want to get the image bytes from it. So we'll just literally take the bytes of the body, and this is just the raw data of the image. And remember, this is the original image on the back end. This is the really large one. Now we can do some image manipulation. So we'll create an image reader, which is a type of the image crate that we imported earlier. And we'll wrap the image in a cursor, which allows us to seek through the data. This isn't something we're going to be doing manually, but it is a requirement of the image reader type. The other thing we'll do is have it guess the format of the image, because this will work with JPEGs or PNGs. Doesn't matter. I think if you add more formats in the features, like we did earlier, then it should work out of the box. And then we will request that it decodes the image. Let's just import these types. Okay, I'll have to import them manually for some reason. Cool. Okay, so we have a type that's going to allow us to interact with the image data now. One of the requirements for the algorithm, as I mentioned, is that the sides are less than 100 pixels each. So we can pull out the width and the height from image dimensions. We can borrow that. And we're going to do the resizing. So yeah, just some math. It's not going to be anything too difficult. If the width is bigger than the height and the width is larger than 100, then we need to resize the image. We need to change the width of the image. So we'll resize it so that the so that the width is larger than 100, but the width is also larger than the height. So we need to change the height and the width, but the width is the larger. So we definitely know that we want the width to be 100, but we need to do some math to calculate the height, which in Rust is going to look a little scary, but it's just because we have to declare the types of the variables that we're calculating with. So we're going to take the height and the width, and we're going to divide the height by the width, and then we're going to multiply the result of that by 100, which should give us the new height of the image. We also want to floor the result of that, because if it is a decimal, we don't want to make the image larger than there is actually data for. So it doesn't matter if we lose a little bit. And finally, we do need to pass into this method an option which describes which algorithm to use to resize the image. In this case, we're going to use the nearest type. And the reason for that is that it is the fastest. And because we're just generating these thumbnail hashes anyway, we don't really mind about the quality of the resulting image.
And we are Fastly, so we want to go fast.
Absolutely. Let me just figure out where I've added too many or too few brackets. Right there. Okay, so that's what we want to do if the width is larger than the height. However, if the height is larger than the width, then we want to do the opposite, which hopefully Copilot is going to understand what we're trying to do here. It is, so we can just go with the suggestion there. And oh yeah, I've put a semicolon on the end of here. We want to return the image, the new image. Resize actually returns a new image. I will format that so it's a little easier to read. So at this point, we now have an image in memory that is less than 100 pixels on both dimensions, which means that it is ready to be passed into the thumb hash function to generate the hash. It is a requirement that we have the width and height to pass into that function. So we'll just do the exact same as what we did up here and set those to variables. And then it's as simple as calling the function. So one of the main functions in the library is RGBA to thumb hash. This takes in a width and a height and an array of RGB data. And this is basically the raw pixels that make up the image. And using the image library, it's pretty easy to get this. We can just call image.toRGBA8, which is what the algorithm is expecting, and we'll convert it into a vector because that is what the function requests. We also need to cast these to the correct type. We can be pretty confident that we're not going to run into panics here. However, in a production app, you're probably going to want to be a bit safer about this. But the ending result is that we have the raw bytes of a thumbnail hash that represents the image. So the only thing left to do is actually just send that hash back to the client. So the result of this function is meant to be a result response. So we'll just go, okay, response from body. The body is going to be the thumb hash exactly as it is, the binary data. And I would suggest adding a content type just to make sure that if someone goes to this URL directly, their browser isn't going to assume that it is something that makes sense. Application octet stream is a great MIME type for this because it just represents any kind of generic binary data. So we're probably not going to get anything massively interesting here, but let's at least visit the path and see if we get some binary data in the console. And that data should hopefully be the thumb hash that represents our image. I'll go into here and pull out one of the URLs. Cool, okay, so it's online. Let's just it's not ever SSL. And we're hoping here that we receive some jumbled up stuff, which is exactly what we've received. So this here, although it doesn't look like it, is a valid thumb hash. We encode it in base 64. It looks something a bit more like the way that you would typically see these, but there's no point in encoding it in a larger format when we're just going to be sending it directly to a client to be decoded. So that takes us on to the next part, which is to add the JavaScript to decode these and display them on the page.
Nice. So we're going to have to make a little script on this index here.
Absolutely. I'm just updating my reference material. So we'll put it at the bottom of the body because we don't really want to block the rest of the page loading. And because we have a dependency that we're pulling in here, that would be the case. We are going to be loading the thumb hash JavaScript library. You would usually want to host this on your own domain. This is pretty easy to do with our Fastly Computer Edge service. But for the sake of getting this done quickly, we're going to be using JS which is a Fastly supported service that allows you to basically import Node.js modules really, really easily from NPM. Not just Node.js, but browser modules, obviously. So we're going to go ahead and import the function from that library. And we're going to wrap all of this code in a event listener. Okay, so just to kind of recap before we get into actually writing the code, the goal here is to go through all of the images on the page once they've been loaded into the DOM and take the placeholder URL that is set as an attribute, make a request to that URL, decode the response, and then use the data from that response as the source for the image. And then finally, when the image gets scrolled into the viewport, we want to do that process again, but instead of decoding the thumbnail from this path, we would just be replacing the image source with the actual image from the origin. So let's do those things. The first thing we'll do is query for all of the images on the page. In this case, we could just do like image because we know exactly what all of the images are, but actually because it's likely that this code will be used elsewhere, it's worth looking for elements that actually have the placeholder attribute. So this is the way that you do that with the CSS selector. You query where the placeholder is not empty, and that will give you back any of them that have placeholders. Yeah, a little wild. I thought you'd just be able to like query for an asterisk, but that's JavaScript. And yeah, we'll let's write some comments so we don't lose track where we are. We're going to loop through all of the images and fetch the placeholder, replacing the image source with the decoded placeholder. So we'll loop through the images and we'll fetch the placeholder. And we can literally just call fetch on the path because we know that this is valid. We set all of these earlier. I'm just going to use promise chaining here because it's a little bit easier to follow. We'll check if the response is okay. And if so, then we're going to take the data from the response. You're probably used to calling like response.text if you've worked with, you know, fetch before, or response.json potentially, but response.array buffer just returns an array buffer of raw binary data that may have been returned, which is perfect for us because we know that that array buffer contains our thumb hash. The function that we imported earlier takes a thumb hash and turns it into a data URL. If you're not familiar with data URLs, they're a way to kind of encode an image or file or piece of content in base 64. And then you can essentially like embed the image as like blah, 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 and the entire image is embedded there. So we're going to use the thumb hash to data URL method to generate a data URL and then replace the image SRC with that new data URL. So that is as simple as calling thumb hash to data URL. We need to wrap the data in a uint8 array just so that it knows what type it's working with. And the final thing we want to do is actually update the image. However, it is possible that by the time that this has happened, the original image has already been loaded in. Perhaps the user scrolled past it and they already had it cached. So we want to make sure that we only set the source if it hasn't already been set. Now, this should be enough for us to load the page and see a bunch of blurry thumbnails. So let's give that a try. There we go. Lots of blurry thumbnails. You can see the data images, data URLs that I was talking about. And if we look at the network tab, we've gone from a 4 megabyte page down to a 10.2 kilobyte page, which is a huge improvement. I mean, you can see the size of the images, thumbnails here. They're absolutely tiny. We're talking hundreds of bytes. So this is a really great start, but of course we do need to actually load the full image when the user scrolls that far. So let's do that part. If you haven't done something like this before, it's actually not as difficult as it sounds. There's a utility in most modern browsers called Intersection Observer, and this allows you to basically be notified when an element becomes visible in the viewport. So we're going to go ahead and create one of those, and we're going to also loop through all of the entries when the observer gets called. We want to see if the entry is intersecting, which is if the element is on the page. And if so, we want to update the source to be the data source. So all we're doing is literally taking this and programmatically turning it into this when it becomes visible on the screen. And the final thing I'll do just to kind of demonstrate what's going on a little bit better is pass in an argument that will make it only load them when it is showing more than 25% of the image on the screen. Another thing we want to do as well is stop observing the image once we have updated it, because we don't want to be running this all the time, especially because this is going to become, well, this isn't going to become null, but we're just going to update that all of the time.
Then you're gonna want to loop through all those images and observe them, yeah?
Absolutely, just like that. And the reason we don't do this in the image loop earlier is because here we're actually firing off a fetch, which takes time. If we made it async, that would be okay. But for now, it's just easier to have the separate loop at the bottom to set up the image observer. Now let's run Fastly Compute Serve again. Go back to the browser. And as I scroll down the page, nothing happens. Images is not defined. That's outside of the function there. That's why. Let's try that again. There we go. So you can see as I scroll, a little bit of the image comes into view. It's a blurry thumbnail, but then as I scroll a bit further, the full image loads into the viewport. You can see in the network tab that those requests are not being sent until I scroll. So this is huge. I mean, we're generating these thumbnails on the fly. We're loading them. It works pretty well. But it does seem a little bit wasteful, especially when we're paying for our compute to go ahead and, you know, load this image into memory every time, resize it, generate the hash. Like, these are all computations that we'd be better off doing just once.
If only we had a way to cache the content that we generated with our compute at edge. If only we had a way.
Is that possible? Is there a product that allows you to do that?
I think there is. I think this is a job for Core Cache.
It definitely is. It definitely is. So if you didn't gather from what we were saying earlier, the Core Cache API allows you to cache content that was generated at the edge. So instead of doing all of this work every time, what we can do is generate our thumb hash and then save it to the cache with the path of the image as the key. So the next time a request comes along for that same image, we can just pull it from the cache. So let's give that a go. In the meantime, we're going to deploy it to a real service. Journey, would you mind explaining why we have to do this?
Yeah, so Core Cache is actually so new that the local testing server isn't supported yet. So we're going to have to deploy this to a proper service in order to use the Core Cache API.
Luckily, it's pretty easy to do that. We're just going to go ahead and add a domain and a backend. We know what the backend is. We know what the name of the backend is. This is a pretty easy service configuration when it comes to Computer Edge. And we'll see now that the service is going to activate, and then the CLI is going to keep kind of pinging it until we get a good response. So in the meantime, let's take a look at the Core Cache API and how it can help us. I'm going to head on over to docs.rs/fastly, which is the Rust documentation hub. It's all of the methods that are available within our SDK. And inside of here, I'm going to go to the cache module. This contains some documentation about our existing HTTP caching, but of course, this is not going to help us here because we are not caching HTTP responses. We are caching things that we have generated on Computer Edge. So we're going to take a look at the core module. The core module has two important main functions, one being insert and one being lookup. And I'm sure you've probably gathered by now, but insert allows you to provide a key and a value and write it into the cache. And lookup allows you to provide that same key and hopefully retrieve that value from the cache. So let's go ahead and do that. We'll quickly check that our app has deployed and is working as it is. And we'll also take a little benchmark at how it's performing now. Oh, I've made a mistake. I've accidentally typed HTTP here, where this should be HTTPS. So we'll go ahead and try that again. And in the meantime, while that's deploying, I guess I'll get started with the code. So we've got two functions to add here. The main thing we want to do is fork the logic here. So right after we've got this image path, we're going to be able to tell whether the thing that we need is in the cache or not. So our end result here is this type. So we'll move this declaration up and then put everything in an if statement, and it should make a lot more sense. So we're going to let thumb hash if let sum entry, and we're going to call Fastly cache core lookup, and the key is going to be just the image path because it's unique for us in this case. If you wanted to add more data to make it more unique, you absolutely can, but this works for us in this case. We'll call execute on that query and we will unwrap the result of the query. And we now know that if this branch is called, then we found a thumb hash in the cache. That rhymes. Otherwise, we need to generate a thumb hash. So let's copy all of the code for generating a thumb hash into that second branch. And instead of saying let thumb hash, we'll just return it as it is. And then the other thing is that we need this to be the correct data. So we're going to turn it into a stream. We're going to unwrap that stream, and then we're going to turn that into the raw bytes. So now what we're doing is before we're generating it, we're checking if it already exists in the cache, and if it is, we're just returning early. But of course, it doesn't exist in the cache because we haven't inserted it yet. So let's add back the thing I just removed. We'll return that at the end so the compiler doesn't complain. But we're going to add one more call, which is obviously to insert. So the way that we do this is by creating a writer. A writer is returned when you call insert. We'll pass in a duration for how long we want this to stay in the cache. For now, we'll just say like I don't know, 1 hour, 24 hours. Doesn't really matter because all of the image keys are unique in this case. And again, we'll call execute and unwrap. Let's see. That's meant to be there. And the other thing we want to do as well is provide the length of the data that we're going to be writing, which obviously we already know because it's the thumb hash that we've just generated. Final thing to do is to write the thumb hash itself to the writer that we just created. And flushing the writer. This means that the key will have been written to the cache. So yeah, that seems correct. Let's take a look at the redeployed service now. It is working. So as you can see now, we're on a live edge compute service. The code without the cache is working. Let's see how long it's taking. So we'll see here, these are the thumbnails loading in. It's taking like 100, 200, 3, up to 400 milliseconds to load these, which, I mean, it's acceptable, but, you know, we can do a lot better. And this is because without the cache, we are just generating these thumbnails every time. But now let's go ahead and deploy the changes that we just made and see how that affects the response time. In the meantime, Journey, would you mind plugging our social medias?
Sure. So yeah, we are once again we're at Fastly Devs on Twitter. We're at devs@fastly.social on the Fediverse. You can find us on our developer blog at dev.to/fastly. And of course, we're on the developer hub, which is developer.fastly.com.
Fantastic. And I just want to say, while we have a few moments, thank you to everyone that has been joining our streams regularly. They've been so much fun, and we've been working really hard to put together a more consistent schedule. So going forward, we're going to be doing these streams every month regularly, and we can't wait to kind of level up, introduce you to some more Fastlians and some more cool computer edge projects.
Yeah, thank you so much for joining us.
So the service has deployed, and you'll see now that these thumbnail requests are taking a lot less time.
Whoa.
25, I mean, even 18 milliseconds. This page with what was 4 megabytes of photos is loading in less than 100 milliseconds. We could shave even more off of that if we were hosting the JavaScript on our own service, but this is just a huge improvement in performance. There are a few tweaks to make. For example, if a client didn't have JavaScript enabled, then they're just going to see empty images because there's no SRC. But there are ways to work around this. We're just kind of here to really show you the power of computer edge and the fact that you can, you know, take an algorithm that was developed for possibly native applications and actually, you know, run it at the edge in somewhere that wasn't expected. And, you know, if you can get these kind of results on reducing image size for free, then why wouldn't you?
Yeah, well done, Kailan.
Thank you. It was a rocky start, but we got there in the end. And
You
you
did
know, the cute cat photos helped us out along the way.
it. Yeah, we'll definitely have to talk to someone higher up at Fastly about creating that pet library.
Absolutely, absolutely. That's everything I've got, I think. Is there anything you wanted to add, Journey, or anything that piqued your mind during the stream?
No. Thanks so much for joining us. Don't forget you can find us on our socials down here and also at Fastly Devs on Twitter. And we will see you on the edge. Bye-bye.
Bye bye.